Hello everybody, and welcome to the top of page 67 in the workbook. We are looking at Theorem 2.22, and this is going to be our development of the so-called change of coordinate matrix, which we first started talking about in the last video. All right, so let's kind of read through this together here. So let beta and beta prime be two ordered bases for a finite dimensional vector space V, and let Q equal blank. We're going to see if we can fill in the blank. Okay, now what is this matrix Q that we're looking for? Well, we'd like it to be invertible, and B actually describes the key property that we'd like it to have. For any vector V and V, we'd like the coordinate vector of V relative to beta to be Q times the coordinate vector of V relative to beta prime. So in other words, what we'd like Q to do is to, if we start with the coordinate vector relative to beta prime, we'd like to be able to multiply by Q and get back the coordinate vector relative to beta. If we scroll back to the previous example for just a minute, that's exactly what this matrix Q that we described there is doing. It's taking us from beta prime coordinates to beta coordinates. Okay, we're just trying to find an actual way of calculating that matrix. Okay, so how do we do that? How do we fill in the blank here? Well, we can kind of reason our way towards that by drawing a picture. All right, so I want to start by kind of illustrating in terms of a picture what we'd like Q to do. Okay, so we'd like it to, if we start with the coordinate vector for V relative to beta prime, we'd like to be able to multiply by Q and get back the coordinate vector relative to beta. Okay, and then we could ask, where do those two coordinate vectors come from? Well, they both come from the same vector V. Okay, and we could go back to our standard representation maps and say that phi beta prime is going to take the vector V to its coordinate vector relative to beta prime, and then similarly, the mapping phi beta is going to take the vector V to its coordinate vector relative to beta. Okay, now I'm hoping that as I'm drawing this, you might say, I've seen this picture before. This seems really familiar. Okay, and so to complete the picture, what we could ask is, what's the linear transformation that takes us from V to itself? Okay, in other words, we can think of the vector spaces up here as being capital V. And so what linear transformation takes a vector as an input and gives back the exact same vector? If you think about it, that's just the identity transformation, IV. And so what this diagram tells us then is that the matrix Q that we're looking for is just the matrix of this identity transformation. Okay, let's write that down. So from the diagram, okay, we see that Q is the matrix of the identity transformation taking beta prime coordinates to beta coordinates. Okay, so we have just discovered what belongs in the blank up here. Okay, so let's go back up to our theorem at the top here and fill it in. So Q is the matrix of IV taking us from beta prime coordinates to beta coordinates. Okay, and so in the next video, we will actually do an example where we calculate this matrix that we just wrote down a formula for.